Today we're going to continue talking about Unit 345, chemical bonding, but we are going to talk about a very important topic in this one, and that is Vesper Theory, which basically tells us the answer to the question, why do they look the way they do? Some things that we need to kind of talk about are some of those exceptions to the rule. And remember that last unit we discussed some of those exceptions to the rule. Heck, even this unit we've talked about some of the exceptions to the octet rule. One of the biggest ones is boron is only going to have 6 electrons in its valence shell. Why is that? Well, it can only have that many. Because if you look at the Lewis dot structure for boron, we would have the Lewis dot structure there. And remember, each dot is a place of bonding. Meaning if I put something else there, and I'm just going to put dots there of a different color to mean that it's of something else, there's no other place that a bond could go. Where else could it be? So the most it can have is 6 in its valence shell. There are some other ones that have odd number of electrons that cannot complete an octet. When that happens, they have what are called radicals. Now, it is not good for radicals to exist. If we have, say, oxygen, and its Lewis dot structure looks like this, and is bonded with something, we would say that that electron right there would be the radical. That makes for an extremely unstable oxygen. Meaning, radicals are not stable. Just like in social gatherings, anything that is a radical usually is an extreme and or not a stable thing. Even though these electrons and these atoms do not have humanistic qualities, I think it helps to put that. These are not stable. We do not want radicals. Instead, we want it to bond with something. We want it to have its octet. We want it to be able to have a bond. When it has its bond, it is no longer a radical. When it is no longer radical, it's stable. It's understandable. It makes sense. And then every now and then, and that's usually comes down to it, is what things that can expand beyond the octet rule. Things that can expand beyond the octet rule are known to go hypervalent. Sulfur and phosphorus are very common elements that go hypervalent. They do not go into hyperspeed. They do not go plaid. They go hypervalent. meaning they expand beyond 8 electrons. If we look at some of the exceptions below, sulfur with 6 fluorine does not look normal, and it's not. Sulfur normally is going to have the Lewis dot structure of this. We would guess that the fluorine would go there, which would be good. However, that's not what happens. There's expands beyond. Because it expands beyond, we have to draw it a little bit differently. And what happens I'm going to put my dots for fluorine in here, because fluorine normally doesn't expand either, but some of the Lewis dot structures or some of the halogens will expand beyond, but sulfur and phosphorus are usually the big ones. Okay, so we can expand beyond. They expand beyond their 8. If we look at sulfur, we can see that there are 1, 2, 3, 4, 5, 6 pairs, meaning a total of 12 electrons. That's crazy. Again, it's gone hypervalent, meaning it's expanded beyond. Sulfur and phosphorus are very common ones that do that. There are others. Be ready for them. Then we talk about Vesper theory. Vesper is just an acronym for a very long term called valence shell electron pair repulsion. Valence shell electron pair repulsion. Vesper theory. And it gives us the shapes that the molecules have. Vesper theory tells us as the electron pairs around the atoms repel each other, which would make sense. Because electrons both have a negative charge, and like charges repel, so they are going to want their space around that central atom as much as they can. And they're going to form some geometric shapes. Some of you might know some of these geometric shapes. Some of you might know it better than others. They will form what are angles. Why did Peterson draw certain things a certain way? Well, it becomes the Vesper theory. There are 2 types of shapes. The electron pair geometry, that's kind of the Lewis dot structures that you were drawing and we were drawing before. And the molecular shape. The molecular shape is just what the molecule looks like. What does it look like? And the molecular shape does not have all of the electrons being shown. So the molecular shape doesn't have all the electrons shown. The electron pair geometry has all of the electrons shown. But again, back to Vesper. So when it comes to electron pair geometry, what we are looking for are the number of electron pairs. Electron pair geometry is usually shorthand written as in EG. And that is the geometry of all the electrons, around the central atom. That should say central atom. And this takes into account both the bonding and the non-bonding electrons. Many of the ones that we deal with in class, we deal with the electron pairs, usually dealing with 4 in class, because that gives us the octet. You will see some of these. The trigonal bipyramidal and octahedral. The sulfur hexafluoride was octahedral. It's a very interesting shape. The molecular geometry, or MG, becomes a little bit different. Here we have to pay attention because it only takes into account those bonding electron pairs. So there's many different options, and you say how many electron pairs are there? Not all of them are going to be bonding. Because not all of them are bonding, their molecular shape and the electron geometry are not always the same. Therefore, again, around that central atom, it is the geometry of only the bonding electrons. The trigonal bipyramidal and the octahedral do break down further. Your book has a more extensive breakdown of them all. In the book that we use in the Brown LeMay and I think we are in the 14th edition. I believe they are tables 9.1, 9.2, 9.3 have much more extensive breakdown of each of these. And I think that's page 348 and 344, 345. Those are your page numbers that you would want to use for that. Those ones are definitely going to help you out for some more extensive ones that require more things that go hypervalent. So how does Vesper theory predict the shapes? Well, we're going to kind of get rid of some of the dots, and some of you will probably like that. Some of you kind of will go with that. And so what we will see is it goes from the dots, and we can kind of look at methane here. that the dots for carbon, we normally put them in a two-dimensional thing, but that's not how it works. As we can kind of see, based on kind of the arrows there, that carbon in itself does not just have those dots at every little spot. In that, in all reality, carbon has those dots at different angles. And even more specifically, where carbon has those dots and how they draw it helps us see the three-dimensional aspect that methane actually has. Because what they're showing is that the top hydrogen is straight up and down. The bottom hydrogen is pointing out at you, and that the two hydrogen on the left and the right are kind of back behind. This can be seen a little bit differently if you look at the molecular model that they have drawn. Now, this slide or this image that shows the progression shows that that is blue for the hydrogen. My molecular model set has yellow for hydrogen. The molecular model sets that that our students usually use have white for hydrogen. It really doesn't matter what the color is. What matters is the shape, and that it's tetrahedral, and that the bond angle is 109 degrees. Now, what gets to be interesting, and what I find very cool, is that if I take a protractor to the molecular models that I have in school, the bond angle is about 110. Well, 109 to 110 is my measured bond angle for something that something is drilled, is pretty good. It's something I'll take, honestly. Because if I can measure this out and it's at, oh look, it's at 110. That's pretty good. That's pretty good. That's pretty it's not completely accurate, but it's not that bad. If the bond angle that is drilled in here in these molecular models is 109 to 1010, well, guess what? 109.5 is where they're all at. And if you look at it, it does have a tetrahedral shape, kind of like a pyramid shape. Well, you're like, well, tetrahedral means 4. Well, guess what? Everyone always forgets about the bottom part as well. So let's try out some easier ones, because that's what's important. Start off with some simple ones. And let's see here. Let's draw some pictures here. I'm going to put some lines in here. So we're going to draw it, and then we're going to determine some of the other stuff. So what we have, the first one is hydrogen and chlorine. Chlorine is going to be our central atom because hydrogen can never be our central atom. So chlorine has to be our central atom. Put our non-bonding electrons in. Now, we can go this route here if you choose. You can go that route, or Or you can start to do this, and some of you might like it. I think it cleans things up a little bit. It helps us identify our bonding pairs and our non-bonding pairs just a little bit better. So, when we look at that and we look around our central atom, actually right there, how many electron pairs do I have around my central atom? So how do we know? Well, we can see, hopefully, that we have a total of 4 pairs, of which one of them is bonding. So I look on the chart and it says 4 bonding. Well, I don't have 4 bonding regions. I have 4 regions, or 4 electron areas. Why it's regions we'll talk about later. One of them is bonding. 3 of them are not bonding, because the ones that are just green are not bonding. And therefore, the electron geometry is tetrahedral. The molecular geometry is linear. And if I look at the molecular model for hydrochloric acid, we can see that it's linear. It's flat. See? Just stop. See? Now, the next one is a matter of drawing. This one is a matter of life and death. We have oxygen. If I draw the Lewis dot structure for oxygen, that's what it would look like. I would put my hydrogen there and there. That's one way of doing it. I don't like that way. It gets messy. I like this way. Like that. Notice I am listening to and paying attention to Vesper Theory. Why am I paying attention to Vesper Theory? Because 1, I have to. 2, there's these electrons up top here are pushing. They repel. They are pushing these hydrogen down. They are not written the way a lot of people want to write them. People that write water like this aren't listening to Vesper Theory. It does not happen this way. It's a pet peeve of mine. It's a matter of life and death. Because if I look at water, I can see that I have a total of 4 regions. 2 bonding, 2 not bonding, meaning it is tetrahedral. I probably spelled that wrong. But the molecular geometry is bent. And this in itself is a matter of life and death. Because water is a bent geometry. It is the bent geometry of water that allows life to exist. Without it, life does not exist. If water was linear, life wouldn't exist. Carbon dioxide doesn't work out so well when you breathe it in. But water is good. Water is bent. It allows for life to exist. So do not draw it out linear. And for the last one, because we've already drawn it out before, methane has 4 regions, all of which that are bonding, and therefore is tetrahedral. Tetrahedral.